So we're moving into chapter 10. It deals with refrigeration. It deals with heat pump cycles. And so we're going to start off with a discussion of the Carnot refrigeration cycle. Did we start off when we studied vapor power cycles? Did we study Carnot vapor power cycle to start that? Yeah. And when we studied gas power cycles, did we start with the Carnot gas power cycle? Sure. Well, this is another starting point of the refrigeration cycles, Carnot. So what do we have is, and you can have it like this, I think it was introduced a long time ago. You have some system operating in a cycle, and for refrigeration, you have to supply some work. And the purpose of it is to remove some heat out of a low temperature reservoir, and because of conservation of energy, you're going to have to dump some heat, QH, to a high temperature reservoir, TH. And one of the main themes of the Carnot, either power cycle or refrigeration or heat pump cycle, is when you're bringing in all of this QL, it all happens at the same TL. It doesn't have like some heat transfer into the cycle at this temperature and then some heat transfer into the cycle at a different temperature. It all comes in, all QL comes in at TL. And likewise, all of the QH goes out at TH. Okay. Well, how do we make this system work? Well, first of all, what we'll have is an evaporator. And then we'll have a compressor. And then we'll have a condenser, and then we'll have a turbine. And they set it up such that it flows not in the clockwise, but this is interesting, isn't it? It flows in the counterclockwise direction, doesn't it? And they also peg state 1 as the input to the compressor. State 2 is the input to the condenser. State 3 is the input to the turbine, and state 4 is the input to the evaporator. And a little bit on why did they choose the name evaporator for that heat exchanger? Well, because what's happening to the refrigerant, the working fluid as it flows through that device? It's evaporating, it's boiling, it's turning into vapor where some of it was liquid before. Okay. How about the condenser? Why did they pick the name? That's what's happening to the fluid, the refrigerant, as it flows through that heat exchanger called the condenser. It's condensing. Okay, right. So maybe we go ahead and talk about the pressure. How about the pressure difference across the condenser? What about the relationship between P2 and P3? P2 and P3. Aren't they the same? That's a standard assumption with heat exchangers, and that's what the condenser is. It's just a heat exchanger. And likewise for the evaporator, P1 is equal to P4. But which pressure is higher? Well, look at the way the flow goes through the compressor and know what the compressor does. The compressor boosts the pressure. So a lot of times they'll split the refrigeration heat pump cycles, and they'll talk about the high pressure side and the low pressure side. There's really only two pressures. The high pressure side and the low pressure. There's not 3 pressures or 4 pressures in a refrigeration cycle like this, even the Carnot refrigeration cycle. Just 2. You could talk about the condenser pressure, that's the high pressure. You could talk about the evaporator pressure, that's the low pressure. Let's spend a little bit of time thinking. If I have the condenser, that's going to be rejecting the heat, Q coming out of the cycle. Q, maybe I put COND there. And for the Carnot refrigeration, it all has to go out at TH. It all has to go out at the same temperature. So what is the difference between T2 and T3? There is none. They have to be the same temperature. as soon as it starts to go into the condenser at T2, it doesn't cool off before it starts condensing. It starts condensing right away. And because it's condensing at constant pressure, the temperature doesn't change. Oh yeah, you're transferring heat out. You're rejecting heat out of the fluid, but it's not changing the temperature. Remember back with Thermo 1, you'd say that's impossible. You know, if you're going to cool something off, you have to lower the temperature is going to come down. No, what we're doing is condensing. Okay. Likewise over here, if you have it all cold and you're bringing in the heat, oops, I just erased that. I'll have to redraw it. What is the difference between the T4 and T1? Well, you need to bring in the heat all at that low temperature, TL. Otherwise, you won't have a Carnot refrigeration cycle. Okay. Well, how do I do that? Well, it's maybe easiest to visualize this on a temperature entropy diagram. Go ahead and put a two-phase region, a dome on there, and maybe put a line of high pressure and a line of low pressure, and see how this could work. This is high, this is low, and you want to be cooling it, rejecting heat from at that high pressure. The maximum extent you could do is, I mean, you're trying to move two red lines, two vertical lines like this, is to push this one as far over as you can, and it would be right there at the limit where it's high pressure, saturated vapor, and then you're going to start condensing, push this one over as far as you can, such that that fixes the other state, what comes out of the condenser at high pressure, that's saturated liquid. So get rid of these. This is where they typically peg state 2 and state 3. So state 2 is saturated vapor. State 3 is saturated liquid at that high pressure. Well, then you think, okay, this is Carnot. I have the best turbine theoretical money can buy, you know, so we're going to have, it's going to have Q of the turbine equal to 0, sigma of the turbine equal to 0. Hence, S4 is equal to S3, isn't it? Isn't it isentropic? So where is that on a TS diagram? State 4 has to be at that low pressure, straight down, and there's state 4. And the hardest one is thinking, where's state 1 at? So it's going to be straight down below state 2 because it is also isentropic compression. S2 is equal to S1. It's the best compressor that you could theoretically ever have. So it's reversible, adiabatic, hence it's isentropic compression. And there's our box. There's our rectangle for our cycle on a TS diagram. Okay. Let's think about a metric of performance. You could talk about, well, first of all, if you were going to analyze a problem like this, we would set up and find a table of properties, wouldn't you? And we would have state 1, state 2, state 3, state 4, and we'd talk about the pressures, temperatures. I would talk about the quality, because definitely 2 of those states are inside the dome, and then the enthalpy and entropy. And after that, I'd get a table of the transfers, energy transfers for each component. I'd talk about the compressor, I'd talk about the condenser, I'd talk about the turbine, the evaporator, and I'd talk about what is the Q in kilojoules per kilogram and what's the specific work for each of those. Now, of those 8 entities, 4 of them are 0, 4 are non-zero, because the turbine and the compressor are not heat transfer devices. So the compressor and the turbine have 0 Qs. And the condenser and the evaporator are heat transfer devices. They're not work transfer devices, so they're 0 and 0. So half of that table is 0. Okay, but then you would get, you would have to calculate these 4 quantities right there. Okay, we would do them by doing an energy balance around each component. First law. The second law we already did. It was pretty trivial. So let's take a look at the compressor. If we go the first law around the compressor, we have to pick. Now what I'm going to do is I'm going to always put the sign convention, so I'm going to put it like this, even though the sign convention I violated over here, talk about both positive QL and positive QH, but here I'm going to try and be consistent with the sign convention for each component. So this would be the work out of the compressor. That's going to be a negative answer right there, right? A negative quantity. So it's going to be the difference in enthalpy. It'll be H1 minus H2. How did I get this H2 over here? How did I get this H1? Well, H2 is pretty easy because 2 is saturated vapor. So it's H of G, the saturated vapor enthalpy at whatever temperature, pressure, the high pressure side. All right. How about this H1? Well, that's a little bit of work. I know that it's isentropic, so these two S's are the same. I know it's pressure or temperature is given, so I know the evaporator condition. And then I have to probably find the quality, and then once I get the quality, I find the enthalpy. Basically, I know maybe pressure and entropy, and then I get the enthalpy. Pressure and entropy. How did I get to S? Because it's isentropic. Second law, that S1 is equal to S2. Okay. Let's go to the condenser. And I know that I showed that positive condenser going out, but I'm going to switch it now. And so Q condenser going into my control volume surrounding the condenser. We know that's going to be negative because it's really heat rejection. But it's going to be the H3 minus the H2. H3 is lower than H2. I'll have a negative quantity, and I'll be able to calculate that. Now, for the turbine, do a control volume around. The positive direction coming out, W out of the turbine. That is truly a turbine, if I could make it work like that, would produce some work out of the cycle. And it would be H3 minus H4. And then for the evaporator, it truly is Q coming into the evaporator. And that's going to be H1 minus H4. So you get all the enthalpies. That's the critical piece of information in the table of properties. And then you can calculate all of these energy transfers. And last, if I can fit it in there, there's a metric. There's multiple metrics, but at least one metric is the key metric for this. And it's called the coefficient of performance. Okay, the book uses, I think, gamma or beta, maybe gamma, I think, for coefficient of performance. Here I deviate from the book. I'm telling you, I'm not going to follow the book. I think the book has made a mistake by introducing a Greek letter and calling that coefficient of performance, when so much of the literature, guess what they use? COP, coefficient of performance. Pretty easy. And then because it's a refrigeration cycle, you put a subscript R on it. When we go to the heat pump cycle, we'll put a subscript HP. I think that's so much easier for students to remember. COP, subscript R, refrigeration cycle coefficient of performance. What's that defined as? Well, I didn't leave enough room, did I? I'll tuck it in down here. What is the coefficient of performance defined as? What do you really want the cycle to do? It's a refrigeration cycle. What do you want the refrigeration cycle to do? Of all of these Q's and W's, what do you really want it to do? A large Q in the evaporator. So you want Q evap, and you want to divide that by what you have to pay for, what you have to provide. And you're going to have to pay, I like to say it like this, pay city public service for the electricity to provide power to the cycle. Basically, you have to provide work to the cycle, energy to the cycle in the form of work. So it's not just the work into the compressor, it's the work into the compressor, subtracted off the work you get out of the turbine, or just do the sum down here and it's W net. That's the W net. Then you're saying, Professor, what about this? Isn't that negative because it's net into the cycle? Yeah, so put a negative sign in front of that. Now everything's positive, and I have a positive COP. Is this a power consuming cycle or a power producing cycle? It's consuming. Yeah. I need to supply energy in the form of work to it or power to it to make it run. All right. Okay, well, there's a lot to cover in that cycle. Why is the Carnot refrigeration cycle not practical? What part of this is the Achilles heel? Because you can't go into, I'm going to buy a new refrigerator, and I say, well, does this use the standard vapor compression refrigeration cycle, or does it have the ultra high efficiency Carnot refrigeration cycle? That's the one I want to buy, and they're not going to be able to sell you one. Right? But we studied anyway. It's the gold standard. It's the best you can do. But why can't we build one of these? Because a turbine that takes in saturated liquid at high pressure, that's good, it's high pressure, puts it out at low pressure, but think about the temperature. It's now really cold. And think about the quality. Maybe it's 20%, 30% quality. It's kind of a liquid vapor mixture. You brought in liquid. This thing doesn't work. We can't buy one of those. Go try and buy one. You can't. So this thing doesn't work. This turbine is hard to manufacture and hard to bring in production. Okay, the next one would be, we learned about pumps and compressors. We learned about happy pumps and sad pumps. And we learned about happy compressors and sad compressors. For a happy pump, what do you feed it? Liquid. And you can get it up to saturated liquid, but don't get it past that where it's got a liquid vapor mixture. The best you can do would be feeding it saturated liquid. Oh, subcooled liquid or compressed liquid, it's even happier, but at the limit it would be saturated liquid. Well, what about a compressor? Happy compressors, you feed it gases. And so at the least gas or at the cusp, it would be a saturated vapor. That would be, now if you fed it a superheated vapor, it would be fine. If you fed it an ideal gas far away from the dome, that would be fine. But the limit would be feeding it a saturated vapor. So right here, you're feeding it a two-phase mixture and hoping it comes out saturated vapor? No. That's not going to work either. So those are the two things which are not practical. These heat exchangers, no problem. Okay. Now, you might say, isn't this heat exchanger kind of magical because the fluid inside the tubes and the temperature that you're driving the heat to is the same? Yeah, I know. So it's when you take heat transfer, it's like, to motivate the heat transfer, I need a delta T and an area, blah, blah, blah. But in the limit, these two temperatures are the same. It just means I need an infinitely large heat exchanger. In practice, people focus on improving efficiency in this area. But for the reasons it's not practical is not so much the heat exchanger and evaporator and the condenser. It's the turbine doesn't exist, and we have an unhappy compressor. Let's talk a little bit. Let's quiz ourselves. Now, the way we'll do this is I'll ask you to raise your hand. I'll call on you. You'll answer one question, and then you can't answer any more questions till we're done with this slide or the next slide as well, okay? This is the game we're going to play. And so I remind you of state 1. Where is state 1? Input to the compressor. Where is state 2? Outlet. Okay. Where is state 3? Outlet of the condenser. Where is state 4? Outlet of the turbine, inlet to the evaporator. So let's start by comparing states 4 and 1. Okay. So which of these is true? Is the pressure at 1 greater than the pressure at 4? Is the pressure at 1 equal to the pressure at 4? Or is the pressure at 1 less than the pressure at 4? Only one of these is true. So, yes. B. You're done. You're toast. You just can now enjoy. Relax. Now for the temperatures. The temperatures are the same. So we have 2 that are out of the game. Now the enthalpies. C. So, all right, we're going to switch to A. So the enthalpy at 1 is higher than enthalpy at 4. That's your answer? Correct. Think about energy. As energy is transferred in, which it is, into the evaporator from the surroundings, it's evaporating the fluid and the energy content of the fluid is higher on the outlet and it's going to be realized by a higher enthalpy. You're done too. Entropy. Yes, sir.
S1 is greater than S4.
So this is A. Right. And the same idea. If I take the Q and I divide by T, isn't that the transfer of entropy into our fluid? Q divided by T. And that's building up, or that entropy has to go somewhere, and it's increasing the entropy of the fluid on the outlet. S1 is greater than S4. So all of those are out of it. So we move to the compressor. So which is true about the pressure? P2 versus P1. Carlos. A. So the pressure at 2 is greater than the pressure at 1. Good. Temperature. A. Temperature at 2 is greater than temperature at 1. Notice that the temperature at 2 is TH. What was the temperature at 1? TL. Right? All right. How about H? Yes. B. Or did you say C? She meant C. She meant C. So the work is coming in. I showed it instead of a negative out, I showed it as a positive in. And then we're boosting the enthalpy of the working fluid. It's going to come out higher enthalpy than what it went in. That's what a compressor does. Very good. You can't participate anymore. All right. S. You got it? Or which one? Okay, B. All right. It's the best compressor. It's adiabatic, completely reversible, hence isentropic compression. So I guess both of you are done because I couldn't figure out who answered. So 2 are out. All right, but we have plenty of opportunities to play this game. So those that are out are still out. And now we go on, and we're now going to compare state 3 and state 2. How about the pressure? Yes, sir. B. Yeah, it's constant pressure device. Okay, next one. T3 and T2 are the same temperature. They're both TH. That's right. How about H? All the way in the back corner. C. So the enthalpy at 3 is less than the enthalpy at 2. That's right. So this is the actual direction of the heat transfer. It's out of the working fluid. The enthalpy is going down. All right. And then S. Yes. Which one did you say? C? Yeah. As well, you could divide that by TH, and then that's the entropy transfer with it. It's going out of the working fluid. The S is going to, at the exit, is lower. S3 is lower. Okay. You guys are making this all look too easy. All right. We have just 3 more. So now we focus on the turbine, and we compare the pressure at 4 and the pressure at 3. C. So pressure at 4 is higher. No, less than. You're right. Pressure at 4 is less than the pressure at 3. Very good. Temperature. Go ahead. C. Yep, this was TL, and this was TH. All right. H's. No rush. Take your time. Somebody has to raise their hand. It hasn't done it yet. C. So the enthalpy at 4 is less than the enthalpy at 3. Yes, this is the positive direction of energy out of the working fluid through the turbine because it's producing some work. Hence, the enthalpy at 4 will be lower than the enthalpy at 3. And the last one, yes, sir. B. So, same idea. It's the best conceptually perfect turbine. It's adiabatic, reversible, hence it's isentropic. Hope that was fun. If you could do this, you're well on your way to be able to set up and solve these problems correctly. Yes, sir.
Can we go back a slide? On the compressor, the H's should be H2 higher than H1, right?
Yes, H2 is higher than H1 on the compressor. H2, the enthalpy at 2, Oh, I circled the wrong one, didn't I? All right, so it's A. It's enthalpy of 2. Hey, that's very good. We give you a bonus. I probably said it right. I don't remember saying it wrong. I just circled the wrong one. Right? Right? So H2 is higher than H1. Thank you very much for the correction. All right. So that coefficient of performance. Now, the coefficient of performance for a refrigeration cycle is that Q that you're bringing in from the low temperature divided by W net. And we go back to the overall system operating in a cycle, and we think, okay, W net's provided, and it's going to be able to pull QL out at TL, and then from the conservation of energy, I have to dump off some QH at TH. What is the relationship between this energy transfer, and this energy transfer? From the conservation of energy, is QH equal to W net in plus QL in? Is that true? Sure. And so you could replace W net by QH minus QL. Maybe you recall seeing that done in the previous, class. So you could put QL divided by QH minus QL. And then you could say, well, this is QL divided by QH, and this is 1 minus QL divided by QH. Nothing to do with Carnot yet. But at this point, if it's all reversible, we could go back to Clausius and his inequality, and then it's an equality if it's completely reversible, and we can replace the ratio of Q's, QL divided by QH, by a ratio of T's. I forget what chapter that's in. Maybe end of chapter 5, beginning of chapter 6, and that inequality becomes an equality when it's completely internally reversible, etc. So this can be now TL divided by TH. Why? This is Carnot only. Divided by 1 minus TL over TH. So you can unravel a little bit. TL divided by TH minus TL. That's what the COP is. COP refrigeration. Not all of the refrigeration cycles, but only the Carnot refrigeration cycle is TL divided by TH minus TL. Somebody shy. They didn't answer any question in the previous slide. I have a question for you. The question is right here. For the Carnot refrigeration cycle coefficient of performance, it's equal to either answer A, B, C, or D. Would you like to try? D. Why do I emphasize this? Because there's probably this equation, the thermal efficiency for the Carnot heat engine is 1 minus TL over TH. Have you seen that equation enough? Did I emphasize you probably are going to see that when you take the fundamentals of engineering exam on your way to become licensed? When should you take that exam? Your last semester here, not after you graduate, the last semester here, or even you could take it the semester before your last. Do not take it after you leave, thinking it'll be better after you leave. It's not. It's like taking medicine after you're already well. Take your medicine when you're sick and get better. Got it? Anyway, the probability of seeing and needing and using that equation on that FE exam is, I would say, at least 75%. It's high. It's high. Guess what? There's its cousin. Its cousin's not going to be up at the 75%, but it's at least 25%. It's probably more like 33%. It may even be 50%. It's pretty high. It's like I can almost guarantee you one of the questions, it'll be using this information on that fundamentals exam. So you want to become very familiar with this equation. Don't pass this class. Somebody thought, oh, what about this 1 minus TL over T? I've never heard of it. Don't do that. or don't not, correctly answer the questions on the fundamentals exam that use this information. Okay, same here. Learn it. Good. Let's press on. Here's a very hard question. And I told the 8 o'clock, or the 8:30, I said, this is a hard question. I'm not going to have people call it out. I'm not going to have people raise their hand. I'm going to de-mic, I'm going to walk around, and I'm going to look at your sheet of paper. And what you answer, A, B, C, or D, right? But this is a hard question. And so for the Carnot refrigeration cycle, the coefficient of performance is always greater than 1, or always less than 1, or always greater than 0, or between 0 and 1. Do not call out any answer. Let everybody work on it individually. Professor, is that the same equation, the COP refrigeration? Wasn't that TL over TH minus TL? Yeah, that's right. Tell me, does A, B, C, or D apply for this equation? I'm going to pause, walk around. Please don't shout it out. So let's go ahead and answer this question. I'd like to just throw out some possible scenarios. Let's say that TL was 300 Kelvin and TH was only, 310 Kelvin. What would the COP refrigeration Carnot be for this case when it's 300 and 310? Would it be 300 divided by 310 minus 300, which is 10, which would be 30? Yeah. So right away, anything that limits it to be less than 1 or something is no good. But let's now push it. This is actually a pretty easy heat transfer problem, isn't it? Wouldn't this be easy? You're just pumping it uphill only 10 degrees K. Now let's make it hard. Now I know you guys can make something really hard. Let's leave TL equal to 300 Kelvin. Let's change TH and make it hard. Really, really hard. What would you suggest for TH? HARD. I could blame it on my stylist. I mean, it's really difficult. It would be hard to do it. You would expect a low COP because it's like pumping water, right? You pump it up a little bit, no problem. Pump it up way high elevation change. Okay, let's throw out 1,000. Somebody threw out 1,000, huh? All right, 1,000 Kelvin. Well, let's say, what is the COP refrigeration Carnot, C-A-R-N-O-T? Well, in this case, it's 300 divided by 700. What's 3/7? 0.4 something? Okay. Does that help? That was a hard question. You would like it to be large. You would like it to be a lot larger than 1. But really on some tough problems, now I'm saying this is an extreme problem. I mean, that's really extreme. It can be less than 1. Now, because of Carnot, it's rarely less than 1. But still, it could be, theoretically. Do you want to solve a problem? All right, let's solve this problem. So we have refrigerant 134A is a working fluid in a Carnot refrigeration cycle. As soon as it says Carnot refrigeration cycle, you got in your mind that compressor, condenser, turbine, evaporator, all the states. Stay with state number 1, 2, 3, 4, etc. The evaporator temperature is given to be 0. So this TL is 0 degrees C, which is 273 Kelvin, isn't it? And then TH, that's the condenser temperature, and that's 48 degrees C, and then you add 273, and you get whatever it is in Kelvin. Let me see if I have calculated that. 321 Kelvin. There you go. Standard saturated vapor, saturated liquid assumption of where it goes in and out of the condenser. Determine the heat transfer to the refrigerant in the evaporator, and there's the answer. It's about 130 kilojoules per kilogram. And then what is the work input to the cycle? Because I emphasize that it's work input, then we kind of brush off that negative sign. If we said the net work out of the cycle, then I would express negative answer on there, but it's a positive 22.93 kilojoules per kilogram. So for every kilogram that goes in the loop, you're picking up in the evaporator 130.4 kilojoules. And for every kilogram that goes in the loop, you're having to supply a work of 22.93 kilojoules. And guess how much has to be dumped off for conservation of energy? You add the 130 and the 22.9, and that's what you have to throw out. But right away, the coefficient of performance. Could you just use these two numbers and calculate that coefficient of performance? Yeah, let me let you do that right now with your calculator. Can you verify that the coefficient of performance using these two numbers is around 5.69? You got it? One confirmation. Let me get a couple more. You have it? 2. Three. Thank you. Let me get a couple more. 4, 5, 6, 7. Very good. Okay, we got 7. Let me do this. That was computed, COP refrigeration is computed by what I desired. I desired a large Q in the evaporator, and then it was the work input, the net work in, and so it was the 130.4 divided by 22.93. Okay. Somebody else says, I wasn't doing it that way. What I was doing was TL over TH minus TL. Should that give us nearly the same answer? Yeah. How many people did it that way? You did it that way? Did you get that answer? Okay, you did. You did. You did. You did. Okay, very good. They're consistent. Okay. Well, let's solve this problem. I'm going to set it up and solve it in Excel. All right. So when I start Excel, I'm just going to go ahead and start solving this problem. It's a Carnot refrigeration problem with the refrigerant 134A. All right. And I'm going to set it up where I solve for the states. And we have 1, 2, 3, and 4. State 1, 2, 3, 4. And we're going to talk about the pressure in kilopascal. The standard format for a table of properties. Temperature in degrees C. And sometimes I like to add a temperature in Kelvin, and let's just add it there. I know it's trivial, but then we're going to talk about the quality and the enthalpy in kilojoules per kilogram and the entropy in kilojoules per kilogram Kelvin. I think those properties will do us well. So we come in and we're told that the temperature is 0 degrees C, and then it's 48, 48, and 0. All right. Now, at state 2, it's saturated vapor, and at state 3, it's saturated liquid. I like to put notes over here to myself in this column. Okay. So if I wanted to know the pressure at 2, which is the same as the pressure at 3, that's the saturation pressure. So that's equal to Psat as a function of temperature for refrigerant 134A using table A10. This is another add-in. I'm going to push it up the Blackboard Learn, and you can use it just like the gas tables. Okay? But I kind of put this is out of table A10, so you should really be able to do it both by hand as well as knowing how to use the software here. And so I'm just going to select that and then shove it underneath. And there you go. So it's around 1252.6 kilopascal. If I drag that lower corner of the cell, I just solve for all those and then do the same thing up here. Right? What I'm going to do is I'm going to put my conversion factor 273 right here. And when I convert these temperatures, this degree C, I'll just add that 273. If I do a F4 on my keyboard, it makes it stay right there with that $E, $2. It won't, as I drag that cell down, it will always stay with that one cell. But the formula will percolate down like that. Okay. So if I would say, somebody says, oh no, we changed the temperature, you could just change it right here and away you go. Okay, so it's saturated vapor, true? So I could get H of G as a function of temperature for my refrigerant 134A, and the temperature I feed it is at 48, closed parent. Somebody asked me, well, how do I know what are my inputs and outputs? Go right up here. Hopefully this insert function, when I have that function typed out, gives me a little help. And so it says the saturated vapor enthalpy in kilojoules per kilogram as a function of temperature in, not Kelvin, but in degrees C, and that's the way that table is set up, A10. All right, so that's how you can check. This is HF as a function of temperature. Hit tab to finish out that equation, go select the temperature, hit return, there you go. We could also do SG for that table using using temperature as an input, and there's our SG, and then SF underscore temperature for refrigerant 134A right there. Those values should be out of the table. If you have your tables, you can double check. If you see a discrepancy, catch my attention and make me stop and fix it. Okay? All right. Okay. If you wanted to, you could put in this is quality of 1 and this is quality of 0. But state 1, how did we know what is its condition? That was what goes into the compressor. We know the temperature and, from the second law, the entropy. So the temperature is already there, 0 degrees C, but this entropy I just copy from S2. So there, now I see temperature and entropy. So I would do it in 2 steps. Get the quality, X as a function of temperature and entropy for the refrigerant. So there's my temperature. And then I have to select the entropy right there. Okay. See how we got the quality? If you want to, we can make that percentage, maybe show more than 1 decimal. So it's 97.6%. And then I get the enthalpy as a function of temperature quality for the refrigerant. And there's my temperature, and that's quality. I think that's the way you would do it by hand. Isn't the sequence of steps? Yeah. Now, right here, I'll just say that's equal to that entropy. And because they're the same formulas, I'm just going to copy those 2 cells and do a paste. And basically, the formula is the same. Get the quality, and then once the quality, it's a 31%, 31.5%, then get the enthalpy. If you want, we can clean up the digits here a little bit. And those digits look pretty good. What do you think? Is that table pretty good for our properties? Let's go ahead and make a table of our transfers. We're interested in Qs in kilojoule per kilogram. We're interested in the works in kilojoules per kilogram. And each component, which component you want to start with? Compressor. Then we'll go to the condenser. Then we'll go to the turbine. Then we'll go to the evaporator. And then we'll have a little room for the sum. Now, let's go ahead and populate half of the table with the zeros. The compressor is not a heat transfer device. The condenser is not a work transfer. The turbine's not a heat transfer. And the evaporator is not a work. Okay. Compressor. I'm going to stay with the sign convention. That needs to be a negative W. But it's related to the changes in H. So it's equal to the H coming in at 1 minus the H going out at 2 across the compressor, negative 29.18 kilojoules per kilogram. Again, I talk to myself when I do this. I'm saying that is into, not out of the compressor. That's why it's negative. Condenser, same thing. It's going to be a negative Q because it's out of the fluid in the condenser. So it's going to be my H3 minus my H2. All right, what about my turbine? This is a positive work, and it's between 3 and 4, so it's H3 minus my H4. And then the evaporator is a positive Qn. It'll be the H1 minus the H4. Whenever I look at this, I say, well, I hope the sum works. I'll just do the sum of those 4 above. That's my Q net. And then the sum of the 4 above for work net. And we look at it. Let's get it to the same number of digits. It's good to 1, 2, 3, 4, 5, 6 digits. Okay, very good. So now let's say, what did we want for the answer for part A? I forgot. Was it our Q in the evaporator? And its magnitude is right here. And the units were kilojoules per kilogram. And this is just my preference, and maybe I'll box it, whatever. Box it and color code it so that it stands out. How about for part B? What was that? For part B, that was our net work. How did I word that problem? But anyway, it's going to be a work net in. So here, I'm going to go ahead and get rid of the negative sign on that work net. So it's kilojoules per kilogram. And then the last is part C, the COP for refrigeration cycle. And that's the ratio of these two. And it's dimensionless. Let me clean up some digits here. All right, so 5.687. What did we have before? 5.69. Okay, so it agrees. All right, so let's go ahead and use our simple analytic expression, which is TL divided by TH minus TL. Remember that? Sure. So we have to put in Kelvin. So there's our TL. We divide it by TH minus TL. And do we get the same answer? What do you think? So it agrees, but it agrees to three digits for sure. All right. Somebody says, I wonder, that's so close. I wonder if you should do 273.15. Will that improve? Hey, what's going on here? That didn't improve it. Well, I had a little discussion with the 830 class earlier, and the deal is how many significant digits are some of these values given to in the table? Let's say you have your table open. You can look at for the line at 48 degrees C, and you could find S. How many significant digits is S given to in that table? 4. And the H's are sometimes given the 5, but the S's are given the 4. All right. Now, you ask yourself, this S of right here is S of F, and this is S of G. If somebody would have said, I'm not going to show you what, let me do this. Let me see if I can play with you a little bit. I'm going to test your knowledge a little bit. I'm going to say, I'm going to give you a lot of information, but I'm not giving you S of G at 48 degrees. I want you to calculate it. Well, you could say, if you let me know what S of F is, then what I'll do is I'll say that S of G is equal to S of F plus the Q that's brought in from the saturated liquid to saturated vapor, Q divided by that temperature. And oh, by the way, that temperature is constant as long as I'm not changing the pressure. So you say, I remember something like that. So S of G is equal to S of F. what is that Q that's being brought in? Isn't that HFG divided by the absolute temperature? Sure. Well, let's check it out. So here's my S of F. And then I'll say, what is my HFG? Here is my H of G to 5 digits. Here is my H of F to 5 digits. And then I'll divide by the temperature, and I'll have to divide by Kelvin. And so there would be a good estimate of S of G. See that? Okay. Now we'll go back and compare, because we only were given that number to how many digits in the table? 4. So what did they do? They dropped that last digit 4. So if you keep all your digits and the table doesn't, then you could get more than 3 significant digits of agreement between the simple equation and the coefficient of performance using the thermodynamic data out of the tables. Long discussion, but some students were really perplexed. They said, "Professor, this is all garbage. I need to see this good to 5 or 6 significant digits." Well, remember some of our inputs, especially this S out of the table, is not good to 5 or 6 significant digits. It's truncated at 4, isn't it? Right? All right, so there you go. With that, I think we're done for today, unless you have a comment or question for me. Let me pause and see if anybody has a comment or question. Thank you very much for your attention. We'll see you later.